So every time you type a 0 on your keyboard or, fire off a quick text message or even just drop a file into a cloud folder, you are actually relying on a piece of technology that ancient mathematicians and linguists basically had to invent out of thin air.
Yeah, and I mean, they obviously didn't do it to build a digital network. They did it to keep the world's first uh, analog hard drives from crashing, basically.
Exactly. Welcome to the deep dive, everyone. I'm your host, and today we're getting into something that really shatters this illusion we all have of absolute modernity.
Right, because we look at our glowing screens and, fiber optic networks across the ocean floor, and it feels like we inhabit a reality that is just entirely divorced from the past.
Yeah, like data is this distinctly modern concept, right? Like it's
Yeah.
just a byproduct of silicon and electricity. But we are looking at a specific section from Ronald Ligarski's book, The History of the Internet, from its foundations to the present.
His whole premise is that before the microchip, before Alan Turing or anyone like that, humanity wasn't just fumbling around in some information dark age.
Right, we usually view the ancient world through this lens of just material culture,
Yeah.
like stone, bronze, iron.
Exactly. Rather than seeing it as a series of incredibly sophisticated information networks,
Right.
the fundamental architecture of our entire digital world, how we encode data, how we store it and retrieve it, that was all engineered thousands of years ago.
Which is just wild to think about. So our mission today, for you listening, is to pull apart that engineering. We are tracing this profound paradigm shift from the ephemeral spoken word to the creation of enduring physical records.
Because if you want to understand how to navigate today's relentless information overload, you really have to understand how our ancestors solved their very first crisis of persistent data.
It reveals the hidden logic behind literally every digital action we take today. So to understand that acceleration, I guess we have to look at the baseline, the legacy system, right?
Yeah, we have to look at how humanity stored information when the absolute only hard drive available was the biological human brain.
Right, where information was entirely tied to the human body.
Ligarski calls this the era of embodied knowledge. In a purely oral culture, information is inherently volatile. I mean, it literally only exists in the physical vibration of air molecules during the brief moment someone is actually speaking.
Wow. Okay, so once the sentence is finished, the data is just, it's gone.
It's gone. There is no external physical record to go back to. So to keep that information alive, to prevent it from decaying, it had to be constantly actively repeated.
I always think of oral tradition in terms of computer RAM, random access memory.
That's a really good analogy.
Because RAM is incredibly fast, right? It's highly dynamic.
Yeah.
A skilled storyteller can recall a history, read the room, adapt the emotional delivery in real time, and weave in all this relevant context on the fly.
Right, but RAM is volatile memory. The moment the power gets cut.
Exactly. The moment the storyteller leaves the village, or, worse, passes away without passing the knowledge on, that data is wiped clean. It seems incredibly fragile.
It does, but they actually engineered the data itself to be structurally memorable. They didn't just speak their histories casually. They encoded them using these incredibly strict formatting protocols.
Wait, like what?
Well, this is where linguistic features like rhythm, rhyme, meter, and melody come in. We look at epic poetry today, like the Iliad or the Odyssey, and we mostly view those features as just artistic choices.
Right, like they just wanted it to sound pretty.
Exactly.
Yeah.
But Ligarski points out they were primarily functional mnemonic devices. The rigid meter of a poem acts as a structural framework. It's acoustic scaffolding for the data.
Oh, wow. So it functions almost like an error correction protocol in software.
Yes. How so?
Like if I'm reciting a poem and I substitute a word that breaks the rhyme scheme, my brain instantly recognizes that the data has been corrupted. The rhythm physically tells me there is a bug in the code.
That is exactly it. The rhythm acts as a checksum. And on top of that, these cultures heavily utilized formulaic language, modular phrases.
Like Homer calling the sea the wine-dark sea every single time.
Right, or swift-footed Achilles. Those repeated phrases provide psychological anchors. They allow the reciter's brain to essentially queue up the next massive block of information while they're delivering the current one.
It's basically buffering.
It's exactly like buffering. But maintaining this biological database required a highly specialized social architecture. You had these dedicated individuals, elders, bards, shamans, whose primary societal function was just to be living libraries.
And because the knowledge was embodied, retrieving the data required a physical gathering, right? You couldn't just query a database in isolation in your bedroom.
No, the act of accessing information was a social event. People had to gather around a fire or attend a performance.
So the community itself functioned as the physical network infrastructure. That actually seems incredibly resilient. I mean, I want to push back slightly on my own RAM analogy here.
Go for it.
While the storage medium, like the individual human, was fragile, the oral tradition network itself survived for tens of thousands of years. It clearly worked really well for preserving core cultural identity.
Oh, absolutely. It was incredibly robust for vertical transmission, passing knowledge down through generations. But Legarsky identifies the critical ceiling of oral tradition.
The bottleneck.
Right. The problem is horizontal transmission and incremental complexity. A biological network struggles with scalability. A human voice can only project so far, and a single bard can only hold so much in their head.
Right, there's a hard storage limit.
And worse, human memory is ultimately fallible over deep time. You get the telephone game effect. Nuance shifts, context is lost, or maybe the political needs of the current generation subtly alter the historical record.
And you can't definitively check the source code. If two elders disagree on a property law from 3 generations ago, there's no master document to consult.
Exactly. It's just one biological memory pitted against another. And that lack of a static reference point makes it nearly impossible to build cumulative, rigorous scientific frameworks.
Because you can't have a multi-generational debate about abstract mathematics if the foundational arguments keep shifting slightly with every retelling.
Right? You can't build a massive intellectual skyscraper if your foundation is always in motion.
Yeah.
So to cross that threshold into systematic knowledge accumulation, humanity had to figure out how to decouple data from the human body.
We needed persistent storage. We had to invent the physical hard drive.
Yes, and interestingly, this transition doesn't start with letters. It starts with highly literal visual representations, pictographs.
So literally just drawing the thing.
Exactly. If a Sumerian temple administrator needed to record that they received an ox, they literally took a clay tablet and drew a stylized picture of an ox head.
Okay, that makes sense. It's a direct one-to-one visual mapping.
And the primary advantage there is its intuitiveness. It bypasses spoken language entirely. An administrator speaking Sumerian and a trader speaking a totally different dialect can both look at a drawing of a fish and agree on the data.
It's the ultimate cross-platform compatibility. But drawing literal pictures runs into a massive conceptual wall the second you try to record human experience beyond just basic inventory. I mean, you can draw a bushel of wheat, but how on earth do you draw the legal concept of a debt?
Or the concept of justice. Or tomorrow.
Right. A strictly literal system is completely incapable of encoding abstraction.
And that limitation forced the first major conceptual leap in data encoding, the evolution from the pictograph to the ideogram.
Okay, so what's the difference there?
Instead of a symbol remaining rigidly tied to a specific physical object, the symbol began to represent an abstract idea associated with that object.
The visual symbol becomes a container for broader meaning.
Exactly. Consider the symbol of a human foot in early cuneiform. As a pictograph, it just means the physical body part. But as an ideogram, that same symbol is abstracted to represent the verbs to walk, to stand, or to carry.
Oh, that's clever.
And Legarsky notes that early scribes began combining these symbols to synthesize entirely new data points. If you combine the ideogram for a mouth with the ideogram for water, you encode the concept of drinking.
Combine the sun with a horizontal line and you get daytime.
Exactly.
This is a monumental shift. For the first time in history, complex, abstract information is successfully living outside of a biological host. It's literally baked into a piece of river mud.
Yes. The person who recorded the thought can walk away, they can die, and that clay tablet will silently hold that data for centuries, just waiting for someone to retrieve it.
So it solves the volatility problem of the oral tradition. But this new solution introduces a new, really severe mechanical bottleneck, doesn't it?
It absolutely does.
Because when I look at ideographic systems, my immediate point of reference is the modern smartphone emoji keyboard.
Oh, that's perfect. Yeah.
Emojis function exactly like digital ideograms. If I text a picture of, like, the folded hands emoji, a pizza slice, and a question mark, you understand the complex request, right? Please, can we get pizza?
Without a single phonetic letter being used.
Right. Emojis are highly efficient for conveying simple states or basic requests, but I could never draft a binding non-disclosure agreement using emojis.
No, definitely not.
I couldn't write a textbook on quantum mechanics using just the thumbs up and the dancing lady. A purely ideographic system just seems entirely unsuited for granular, highly complex intellectual work.
And Legarsky highlights this exact processing bottleneck. The fundamental flaw of an ideographic system is its total lack of modularity. Because each symbol represents a whole word or concept, you have to continually invent new symbols to express new ideas.
So the system just bloats.
It blows enormously. As Mesopotamian and Egyptian societies grew more complex, early cuneiform and hieroglyphic dictionaries expanded to encompass thousands and thousands of unique characters.
Which means a human being has to physically memorize all of them to even interact with the data system.
Exactly. The cognitive load required to read and write became astronomical. Literacy was not accessible to the general public at all. It demanded years of rigorous, dedicated training.
So it birthed the highly specialized scribal class.
Right. Scribes became the elite gatekeepers of the data network. They were essentially the system administrators of the ancient world. So, while clay tablets provided the persistent hardware, the software, the encoding system itself was wildly inefficient.
It was begging for a better compression algorithm. We needed a way to stop creating a new visual symbol for every single abstract idea in the human imagination.
We had to stop drawing ideas and start drawing sounds.
Which brings us to the alphabet.
Yes. Library calls this the most elegant technological pivot in history. The conceptual breakthrough here is the realization that human speech, despite its infinite variety of meanings, is actually constructed from a very small, finite set of basic sounds. Phonemes.
Right. You don't need a symbol for the concept of a house. You just need symbols for the acoustic sounds your mouth makes when you say the word house.
Exactly. And this transition wasn't some overnight revelation. It was driven by intense economic pressure. Library traces the critical turning point to the Levant, specifically with the Proto-Sinaitic scripts, which were heavily adapted by the Phoenicians around 1200 BCE.
The Phoenicians were the maritime traders, right?
Yes, the dominant traders of the Mediterranean. They were managing vast, complex supply chains across different cultures, different languages. They did not have the time or the resources to employ specialized scribal bureaucracies using thousands of cuneiform characters just to log timber shipments.
They needed a lightweight, agile data protocol.
Exactly. Economic incentive drove the technological innovation. The Phoenician alphabet stripped the complexity down to just 22 distinct symbols, all representing consonant sounds.
Wow, just 22. By isolating the phonemes, they decoupled the written symbol from any visual meaning entirely. Like, the letter B doesn't look like a house or an ox. It is purely an abstract representation of a sound.
Right. Now, the Phoenician system lacked vowels. You had to infer the vowel sounds based on context, which actually still persists in modern Arabic and Hebrew writing systems. But even without explicit vowels, reducing all of human thought down to 22 characters was an unprecedented feat of data compression.
It's the ultimate modular system. It functions exactly like a box of standard Lego bricks.
Oh, I love that comparison.
Because with an ideographic system, society is essentially custom molding a highly specific toy for every single concept. You have a mold for a dog toy, a mold for a sun toy. If you encounter a new concept, you have to build a whole new mold.
Which is wildly inefficient.
But the alphabet provides a tiny box of standardized, identical blocks. In English, we have just 26 blocks. But because they represent sounds rather than meanings, you can combine and recombine those same 26 blocks in infinite permutations to build literally anything.
You can use the same 26 blocks to build a grocery list, or the federal tax code, or a Shakespeare sonnet.
Exactly. The Lego analogy perfectly captures the power of modular abstraction.
And Library argues that the consequences of this modularity altered the entire trajectory of human cognition. The first immediate impact was the democratization of the data network.
Because you only had to memorize 24 symbols instead of 2,000.
Right, so basic literacy became attainable for a much larger segment of the population. The steep barrier to entry was obliterated. It broke the absolute monopoly of the scribal elite.
You no longer needed a degree in computer science to use the machine. You just needed to learn a really simple user interface.
Precisely. And the second, perhaps more profound consequence was the capacity for high-fidelity abstract thought. When the Greeks adopted the Phoenician script, they made a critical structural addition.
They added the vowels.
Yes. They repurposed certain unused consonant symbols to explicitly represent vowel sounds. This created the first fully phonetic alphabet capable of recording the exact acoustic reality of spoken language without any contextual ambiguity.
So you don't have to guess the word based on the consonants anymore. The exact pronunciation and tense are hard-coded into the text.
Right, and with that level of precision, a writer can encode extreme nuance. They can record complex conditional logic, abstract philosophical arguments with absolute clarity. Library argues this robust encoding protocol is what truly facilitated the explosion of scientific and philosophical thought in ancient Greece.
The alphabet provided a cognitive tool sharp enough to parse the complexities of the human intellect. And Library draws a direct theoretical line from this invention to the architecture of modern computing, doesn't he?
He does, yeah.
Huh.
By proving that you can take the infinite complexity of human experience and compress it into a finite set of abstract characters, the creators of the alphabet laid down the exact logical framework that governs digital logic today.
Because a modern computer processes every image, every audio file, every complex software program using an alphabet of only two characters, 1 and a 0.
Exactly. Binary code is simply the ultimate, most compressed iteration of the alphabetic principle. We invented digital logic the moment we separated the symbol from the meaning and started combining abstract units.
That's just mind-blowing. But the alphabet only solved the problem of encoding language. And language is only one half of the data equation, right?
That's right. As civilizations scaled, as trade networks expanded and architecture got more ambitious, early societies crashed headlong into a secondary data crisis.
They had to figure out how to reliably record and manipulate quantity. They had to invent the mathematics of data processing.
Exactly. Encoding language is about capturing thought, but encoding math is about capturing physical reality. And according to Library, the evolution of numeric notation was an equally fraught process. It starts in the most basic biological way possible.
Callimachus.
Yes, one-to-one physical mapping. For tens of thousands of years, humans relied on physical counting tools. You use your fingers, your toes, or you place pebbles in a pouch.
And the archaeological record actually provides striking evidence of this, right?
Oh, absolutely. Library points to the Ashango bone, which was discovered in the Democratic Republic of the Congo. It dates back roughly 22,000 years. It's literally a baboon fibula covered in structured groupings of carved notches. It is a clear, physical manifestation of early humans externalizing numerical data, probably tracking lunar cycles or seasonal changes.
But a tally mark suffers from the exact same scaling issue as the pictograph. It's a strict 1-to-1 ratio.
Exactly. If I have 5 sheep, carving 5 lines into a bone is easy. If an empire needs to audit a granary containing 30,000 bushels of wheat,
Carving 30,000 lines is physically impossible and completely unreadable, even if you did it.
right. So to manage larger quantities, civilizations had to invent systems that grouped numbers. The Sumerians, who gave us cuneiform, developed a highly complex sexagesimal system, which means it operated on a base of 60.
The Sumerian-based 60 system is one of the most fascinating technological hangovers in human history. We are still deeply entangled with it today.
You really are. Every time we look at a clock and see 60 seconds in a minute, we are using Mesopotamian math.
Every time a navigator calculates the 360 degrees of a circle, they are relying on a Sumerian data structure. It was clearly an incredibly successful way to divide and measure reality. But it begs a massive question.
That is.
If base 60 was so robust that it survived for 5 millennia, why wasn't it the mathematical foundation that eventually sparked the digital age? Why didn't our computational evolution utilize this system?
That is the key question. And the answer is that it failed to scale computationally because the Sumerian-based 60, much like the Egyptian-based 10 system that followed it, was fundamentally additive.
Additive, okay, meaning the symbols represent fixed values, and to read the number, you simply tally up the total value of all the symbols present.
Yes. To understand the friction of an additive system, just look at Roman numerals, which dominated Europe for centuries.
Yeah.
They used distinct letters for different magnitude groupings. I is 1, V is 5, X is 10.
Right, so if you want to write 33, you write x of 3. You are literally adding 10 plus 10 plus 10 plus 1 plus 1 plus 1.
And it's highly intuitive for basic inventory. You can look at a ledger and easily tally up the distinct symbols. It's perfectly functional for static record keeping.
But try executing a dynamic mathematical operation.
Exactly. Imagine trying to perform long division or calculate compound interest on a massive trade loan using Roman numerals.
That sounds like an absolute nightmare.
The physical mechanics of the calculation become impossible. You can't just shift columns or use algorithms. You have to constantly convert, group, and unpack different symbols.
So additive systems create immense computational friction. They are functional for tracking data, but they are dead ends when it comes to processing data at scale.
Yes. And furthermore, Library emphasizes that these early additive systems suffered from a fatal architectural flaw. They lacked a conceptual representation for 0.
They had no way to quantify nothing. Nothing was simply an absence, just a blank space on a tablet. It wasn't a mathematical entity.
And without a structural placeholder for 0, Higher-level mathematical operations are just plagued by ambiguity.
So how did we get past that roadblock?
It was finally dismantled by a conceptual breakthrough originating in the Indian subcontinent. This breakthrough provided the final, critical piece of the data processing puzzle, the Hindu-Arabic numeral system.
And this system introduces two distinct revolutionary innovations, right? The first being positional notation.
Exactly. In an additive system, an X means 10, no matter where it is written on the page. But in positional notation, the value of a symbol is entirely dictated by its physical location within the number sequence.
Right, we use only 10 symbols 0 through 9, but in the number 222, the digit 2 means three completely different things based on its place.
Yes, the 2 on the far right represents 2 units. The 2 in the middle represents 2 tens. The 2 on the left represents 2 hundreds. The magnitude scales by powers of 10 simply by shifting the symbol one column to the left.
It's a massive cognitive leap. You are separating the symbol from a fixed value and allowing the structure of the sequence to define the data. It's infinitely scalable. You can represent the national debt or the distance to a galaxy using the exact same 10 symbols.
But to make positional notation function reliably, you absolutely require the second innovation. You need a structural mechanism to indicate when a column is empty.
You must have a placeholder. You need shunya.
Shunya. The Sanskrit word for void or empty, the invention of the symbol for zero.
Culturally and philosophically, conceptualizing nothing as a tangible entity was incredibly difficult for a lot of societies, wasn't it?
Oh, very much so. Many early philosophical frameworks, particularly in the West, actively resisted the idea of a void. Nature abhors a vacuum, right? But Indian mathematicians recognized that nothing wasn't just an absence, it was a mathematical necessity.
Because if you're using positional notation and you want to write the number 405, you have a 4 in the hundreds column and a 5 in the units column. But the tens column is empty.
And if you don't have a symbol to anchor that empty space, the 4 and the 5 collapse together into 45. The entire data structure disintegrates without a structural pillar holding the empty column open.
The structural necessity of zero maps perfectly onto modern computing hardware. Think about the concept of empty space on a computer's physical hard drive.
Oh, that's a great point.
When you delete a file, the computer doesn't physically destroy the disk. It just designates that space as empty. But it literally represents nothing. There is no user data there. However, without the ability for the operating system to mathematically define and track that precise nothingness, the entire file system would crash.
The computer cannot write new data if the mathematical architecture doesn't understand exactly where the empty space is located. Zero isn't just a philosophical concept, it is a load-bearing architectural requirement.
By providing a placeholder for nothing, zero unlocked the capacity for algorithmic calculation.
It removed the friction of additive systems. It allowed mathematicians to execute elegant, rapid calculations by simply manipulating columns of symbols. Library traces how this system was picked up by Arab mathematicians during the Islamic Golden Age.
Scholars like Al-Khwarizmi, right?
Yes, whose Latinized name literally gives us the modern word algorithm. He used this system to develop algebra and advanced astronomy, and it eventually filtered into Europe, completely revolutionizing commerce and engineering.
So Ligarski's ultimate thesis here is that the digital age didn't begin with microchips. It began with these dual theoretical breakthroughs, the phonetic alphabet and the Hindu-Arabic numeral system.
Exactly. They established the exact theoretical frameworks of abstraction, modularity, and algorithmic processing that modern computers execute at the speed of light.
So we solved the encoding problems. We had the phonetic alphabet and we had algorithmic mathematics. Armed with these robust tools, humanity began generating an unprecedented volume of persistent physical data.
We were writing down legal codes, mapping stars, drafting literature. We successfully externalized human memory on a massive scale.
But solving the encoding and storage problems immediately triggered the third great crisis of information technology, didn't it?
It always does.
Generating massive amounts of persistent data is completely useless if you can't actually locate the specific piece of data you need. A massive warehouse full of unmarked boxes is just a fire hazard.
That is the crisis of scale. And it ushers in the era of early data centers.
Because as civilizations shifted their storage mediums, moving away from heavy clay tablets toward lighter materials like Egyptian papyrus and parchment, the physical footprint of data shrank.
Which allowed institutions to stockpile vast, centralized collections of scrolls. The volume of data exploded.
And as the volume scaled, the primary engineering challenge shifted. It was no longer a struggle to store information. The struggle was navigating the archive.
Right. If you have 10 clay tablets, you could just look at them. If you have 10,000 papyrus scrolls stacked in a room, you have a critical retrieval problem.
We needed a scaffolding for knowledge. We needed metadata.
And we see early attempts at this scaffolding with Greek philosophers like Aristotle. He recognized that the sheer volume of human knowledge required a systemic architecture. He became one of the first great taxonomists.
But the pinnacle of early data management, the physical manifestation of this architectural struggle, was the Library of Alexandria, wasn't it?
Oh, without a doubt. The library was designed to be the ultimate centralized server. The ambition of the Ptolemaic kings was to gather a copy of every single text in the known world in one physical location.
I read that ships arriving in the harbor were reportedly searched, and any scrolls found were confiscated, copied by scribes, and the copies returned while the originals were kept.
That's the legend, yeah. But the physical reality of that ambition is staggering. We are talking about hundreds of thousands of papyrus scrolls. And they weren't bound books with spines and titles printed on the side. They were just rolled up tubes of plant matter.
A scroll doesn't naturally present its metadata to the user. You can't just glance at a pile of tubes and know what's inside.
Exactly. To make that staggering volume of information usable, the scholars at Alexandria needed a retrieval system. And a scholar named Callimachus took on this monumental task.
He developed an architectural framework called the Phoenicianalphabet, right? Which translates to tables.
Yes. And Ligarski emphasizes that the Phoenicians was not merely a physical inventory list to ensure scrolls weren't stolen. It was a highly sophisticated indexing and cross-referencing system. Callimachus categorized scrolls by overarching subjects: rhetoric, law, epic poetry.
And within those categories, he alphabetized by the author's name. But he didn't stop at just sorting them into buckets, did he?
No, Callimachus created robust metadata tags for every single file in the archive. The Phoenicians recorded the author's biographical details, a summary of the text, the opening words of the scroll.
The incipit.
Yes, the incipit, which served as a unique identifier. And he even recorded the exact physical line count of the document, which acted as a data integrity check to ensure a scribe hadn't accidentally omitted a section during copying.
Callimachus was physically engineering the ancient world's first search algorithm. Think about how a modern search engine operates. When you type a query into a search bar, the engine doesn't actively read every single website on the internet in that millisecond.
That would require impossible bandwidth.
Exactly. Instead, the algorithm scans a precompiled index. It is searching the metadata, the tags, the categories, the summarized structural architecture of the web.
And Callimachus was building the analog prototype of that exact metadata index. He recognized that separating the index from the raw data was the only way to achieve rapid information retrieval.
The Phoenicians established the foundational principles of library science and data architecture. It proved that knowledge must be structured to be accessed.
And this manual indexing tradition became the backbone of institutional memory. Ligarski tracks how these principles were meticulously maintained by medieval monasteries. The scriptoriums weren't just copying Bibles, they were functioning as analog data centers.
Grappling with version control, categorizing manuscripts.
Exactly. And later, during the Renaissance, the grand institutional libraries adopted and expanded these systems. The manual card catalogs, the rigorous metadata tagging, these were all analog attempts to solve the precise problems of searchability that modern cloud providers tackle today.
The architecture of the internet didn't invent the concept of structured metadata. It simply automated Callimachus's Phoenicians and executed it at an incomprehensible speed.
The through line is just undeniable once you see it.
It really is. We have basically walked through a 5,000-year engineering process today. Humanity started with the volatile biological memory of oral storytelling, where data lived entirely in the acoustic rhythm of a song.
Requiring constant human repetition just to survive.
Right. And to achieve persistence, we engineered the first read-only memory through literal pictographs, which eventually abstracted into ideograms.
But ideograms created a massive processing bottleneck,
Which forced us to invent the ultimate data compression algorithm, the phonetic alphabet, modularizing all human language into standardized sound blocks.
while simultaneously struggling to map the physical world, moving from crude tally marks to additive systems.
Before finally achieving the algorithmic power of positional notation and the structural zero. And then, when the volume of this new persistent data threatened to overwhelm us, scholars built the first metadata search engines in the scroll rooms of Alexandria.
Ligorsky's history demonstrates perfectly that digital technology isn't a rupture from the past. It is the culmination of a continuous, unbroken lineage of human ingenuity.
We have been striving to externalize our memory, compress our thoughts, and network our minds since the first stylus was pressed into wet clay. It is a remarkable legacy.
It absolutely is.
But, diving into Ligorsky's text leaves me with one final, deeply provocative thought regarding the material reality of our modern networks. We pride ourselves on the permanence of our digital footprint, right?
We do, yeah. We think the cloud is forever.
But today we rely on incredibly fragile physical infrastructure. Our entire societal memory, our financial systems, historical records, personal communications is stored on server farms that require immense cooling systems and a continuous, uninterrupted flow of electricity.
Right, a severe solar flare or an electromagnetic pulse or a total grid collapse could theoretically wipe out decades of human data in an instant.
The medium is hyper-efficient, but it is materially precarious. Meanwhile, the baked clay cuneiform tablets of the Sumerian administrators, the very first hardware our ancestors used to store abstract thought, have survived perfectly intact, buried in the harsh sands of Mesopotamia for 5,000 years.
They require zero power source to maintain their data integrity.
Exactly. It forces a sobering realization. In our relentless, brilliant quest for processing speed and global interconnectivity, we have engineered an information system that is vastly less persistent than the mud used by the very first accountants.
Wow, that is a heavy thought to leave on.
It makes you wonder what exactly will be readable of our civilization in 5,000 years. Anyway, thank you for joining us on this deep dive into the source material. We hope this encourages you to view the digital tools in your hands not as modern magic, but as the latest iteration of an ancient, ongoing human struggle to preserve our collective memory. Think about Callimachus the next time you use a search bar, and think of the ancient mathematicians the next time you type a zero. You are participating in a very old conversation. Catch you next time.